everyone. In this video, we're going to look at the nature of the roots of quadratic equations, so the solutions of the quadratic equations. So we're going to start by considering the equation x squared minus 2x plus 2. Now, typically, I'm going to start by trying to factor to see if that's possible, but nothing has a product of 2 and a sum of negative 2. So I'm going to go to the quadratic formula. Now, recall the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So in this particular case, where a equals 1, b equals negative 2, and c equals 2, we've got x equals negative 2, which is 2, plus or minus the square root of b squared, which is 4, minus 4 times 1 times 2, which is 8, all over 2 times 1, which is 2. But what we notice when we do this is we get 2 plus or minus the square root of negative 4 all over 2. Now, the important thing to note here is if I'm trying to solve these with real numbers only, there are no real roots because this square root of negative 4 does not give a real number. However, we do have two what are called complex roots. So complex roots are sometimes called imaginary, but complex is the more technically correct term. Two complex roots in the form a plus or minus bi, where I is defined as the square root of negative 1. So instead of limiting ourselves to real numbers, we introduce a new number. This is the imaginary number. These roots are called complex because they include both an imaginary part and a real part, the a value. So I is defined as the square root of negative 1. So in other words, what I know then is, as an example, if I have the function y equals x squared minus 2x plus 2, this has no x-intercepts because there are no real solutions here, so there's no real values, so no graphical, physical values where I could have this function crossing the x-axis, but there are numbers that give me solutions to the equation, and those numbers would be complex. So we still do want to simplify this. So in other words, I can express this as 2 plus or minus the square root of 4 times the square root of negative 1. I can split that root part up into the real component and the imaginary component. So 2 plus or minus 2i over 2, which simplifies to just 1 plus or minus i. So 1 plus I is one of the solutions, and 1 minus I is another one of the solutions. If I were to substitute those in, I would get 0. So let's look at another example. We have the equation is times 2x squared plus 3x plus 5 equals 0. Again, try to factor first, but nothing multiplies to 10 and adds to 3, positive 10 and positive 3. If it was negative 10, then that would work. So I'm going to go to the quadratic formula. So x equals negative 3 plus or minus the square root of b squared minus 4 times 2 times 5, which is 40, all over 2 times 2, which is 4. So this is negative 3 plus or minus the square root of negative 31 over 4. So I have two complex roots again. I can't simplify it quite as nicely as the previous one did, but I still do want to simplify a little. I don't want to leave that negative inside the square root. I want to use I. So I have x equals negative 3 plus or minus, so what I'm going to consider is that this is the square root of negative 1 times the square root of 31. The square root of 31 can't be simplified at all, but square root of negative 1 I am going to express as I root 31 over 4. You can leave it that way, but if I wanted to write it in the form a plus or minus bi, I could split that up a little. A is negative 3/4 plus or minus root 31 over 4 times I. So in that particular format, a is negative 3/4 and b is root 31 over 4. All right, so for every equation in the form ax squared plus bx plus c equals 0, so a quadratic equation, where a, b, and c are rational numbers to begin with. So we're starting with a quadratic equation in which a, b, and c are rational numbers. Honestly, more likely we're going to have always just whole numbers, because if I had fractions, I could multiply them through by a common denominator to get whole numbers. But the important thing is they have to be rational. If we end up with irrational and or complex roots, they're always found in conjugate pairs. So in other words, if I have, let's say 5 minus 3 root 7, if that is a root, then 5 plus 3 root 7 is also a root. And that's if they're, say, irrational. If I have 2 minus 6i, if that's a root, so a complex root here, then 2 plus 6i is as well. And that's because the roots are negative b plus the square root of b squared minus 4ac, and it's that square root where either I or an irrational number is going to come from, over 2a. Well, then I have negative b minus the square root of b squared minus 4ac over 2a. So if I know one of the roots is irrational, then I know the other one has to be its conjugate. If I know one of the roots is complex, then the other one has to be its conjugate. And we can always determine the nature of the roots of the quadratic equation, in other words, what kind of numbers we have, by using the discriminant. So the discriminant is the part inside the square root, b squared minus 4ac. It's called the discriminant because it allows us to discriminate between the different types of roots. So for example, if b squared minus 4ac is less than 0, we have complex roots. We have imaginary numbers. If b squared minus 4ac equals 0, we have exactly one root. And that's because, and it's going to be rational. And that's because if I have negative b plus or minus the square root of 0 over 2a, well, whether I'm adding or subtracting 0, I'm not changing it, so it's just negative b over 2a. So that would be what the one root is. And if b squared minus 4ac is greater than 0, then we have two cases. We have if b squared minus 4ac is a perfect square, so a square number like 49 or 121 over 4, the roots are rational. So we'll end up with no square root left over. And if not, the roots are irrational. So if we end up with just about any other number, like 31, for example, then we'll end up with irrational roots in conjugate pairs. So one more thing, and then with all of this information, we can find quadratic equations knowing what the roots are. So the sum and product of roots. So what happens if I add the two roots of a quadratic equation together, and what happens if I subtract them? So considering sum, and this is a symbol for sum, it's an uppercase sigma. So remember that the roots are negative b plus the square root of b squared minus 4ac over 2a, and negative b minus the square root of b squared minus 4ac all over 2a. So I have the same denominator, so I can just add these together. Because I have plus the square root of the discriminant minus the square root of the discriminant, they cancel each other out, and we end up with negative 2b over 2a. The 2's will cancel, so we end up with just negative b over a. This is always the sum of the two roots of a quadratic equation. So no matter which two answers I've gotten, if I add them together, it's going to be the same as negative b over a. And for the product, so capital pi is symbol for product, so negative b plus the square root of b squared minus 4ac all over 2a times negative b minus the square root of b squared minus 4ac all over 2a. When we multiply these together, distribute those two numerators, this is going to end up being over 4a squared. But this ends up being essentially a difference of squares. So when I multiply negative b times negative b, I get b squared. When I multiply the outside and inside terms, so these two and these two, I get opposites. One is going to be positive, one is going to be negative, so they cancel. And when I multiply the two square roots together, I just get the discriminant. And it's minus b squared minus 4ac. So b squared minus b squared, that's going to go away. Minus negative 4ac becomes 4ac all over 4a squared. which simplifies to c over a. So that is always the product of the two roots. So now knowing that my answers come in conjugate pairs and knowing what the sum and product are, I can answer this type of question. So a quadratic equation has a root of 2 plus 3i. What could the equation be? If I know it has one root of 2 plus 3i, then I know the other root is 2 minus 3i. And I can figure out what the sum and the product are by adding these two together and multiplying them together. So the sum, well, 2 plus 3i plus 2 minus 3i plus 3i minus 3i cancels, and we're left with just 2 plus 2, which is obviously 4, and that is therefore b over a. For the product, I'm multiplying 2 plus 3i times 2 minus 3i. So again, difference of squares. So I get 4 minus 9i squared. But by definition, I squared is equal to negative 1, which means I have 4 plus 9, or 13, and that is c over a. Now there's technically an infinite number of solutions here depending on what I choose for my a value. So let's say, to start, that I'm just going to let a equal 1. So I'll find an equation where a equals 1, and just for illustration, I'll also find an equation where a does not equal 1. So let's say a equals 1. That means b over 1 would have to be 4, which means b equals 4. And c over 1 would have to be 13, which means c equals 13. So that means that the equation could be 1x squared plus 4x plus 13 equals 0. So this equation has a solution of 2 plus 3i. But I didn't have to pick a equaled 1, so let's just, for argument's sake, say what if a equaled negative 3, just as an example. You can pick literally any number here. So if a equals negative 3, then that means b over negative 3 equals 4, or b equals negative 12. And it means c over negative 3 equals 13, which means c equals negative 39. So in that case, the equation I would get would be negative 3x squared minus 12x minus 39 equals 0. This equation also has a root of 2 plus 3i. Now I can see why that would be equivalent, because if I divided this second equation by negative 3, I would just end up with the first equation again.